Okay, so when was it? 3 weeks ago, two. We almost finished the topic of electron-electron interaction. So we'll finish that and move to other condensed matter systems that have that we can treat with the second quantization and see how it's implemented. Hopefully, although I'm a bit doubtful, we'll get to the point of superconductivity, but if not, at least we'll do Luttinger liquid and Hubbard models. And okay, so let's start. At the end of our previous lecture, we were at a point where we actually wrote down the interaction term. Okay, and we understood what's happening here with the 3 indexes, 3 and not 4, for the simple reason that we have momentum conservation, and we tried to perform a Fourier transform of the Coulomb potential, and ended up with where when we're taking epsilon, which was a parameter that we put in just to be able to perform the integration, and that was the problem that we remained with. Okay, let's look a moment a bit more closely on the term when Q is equal to 0. Because if Q is not equal to 0, no problem. It's finite, we can perform any calculation. So Q is equal 0. We're setting it at 0. And ever. In this case, I'm just copying what's written above, setting Q equals 0. Okay. I just wrote separately the cases where k is not equal k prime, and the special case where k prime is equal k. Why? Because here I have to be a bit more careful. Okay, I replace this term using the anti-commutation relation. Okay, so what do we have here? We have here a term that actually, if we will define a Gaussian, meaning a spread of the positive charge, which is spread evenly everywhere, this term will fall off, and we have no problems. Okay, let's go back to basic physics. If I'm taking charge, certain number of electrons, and I'm putting it in space, what will happen to this charge?
Single charge?
No, a whole bunch of charge. A spread of charge. N electrons.
So it's great.
They'll just run away to infinity if they can. So how come we have metals that we say that there are free electrons there?
We have positive charge.
Exactly. If the positive charge wouldn't have been there, we wouldn't have electrons there. So these terms simply can be cancelled out by a positive, equally spread positive background, which is known as a Gaussian. If you remember Thomson's model of an atom, that was his model. Everybody understood that there has to be a positive charge somewhere there to keep this whole business together. His guess, which turned out to be wrong, was that it's basically the whole atom has a spread of positive charge. But for the usual situations that we see in condensed matter, for example, free electrons in a metal, de facto, or as a good approximation, instead of looking on the lattice of positive charges, it's not such a bad assumption to assume that we have just a uniformly spread positive charge, and that at least solves this problem. Okay, so I want to move now. Solving these models with two particle interactions, for most models, is impossible to do exactly. You just can't diagonalize them. Because if you're happy with the K bases, it's bad for the interaction, and vice versa. So basically you have to do perturbations. Hopefully we'll get at least to see the beginning of what is done with perturbations towards the end of the course. But there is one unique case, which is one-dimensional interacting systems where an exact, or at least close to exact solution exists. And that's what we're going to see now. Somebody knows how it's called? One-dimensional interacting electron systems? Luttinger liquids. And I assume that if any one of you have said either in colloquium or in a seminar, he or she heard this term at some point.
Could you repeat the term?
Luttinger.
Luttinger?
Yeah. I'll write it down in a moment. Yeah. כל מיליארדי הצופים בעולם לא יבינו, אבל...
כל הדבר הזה הזכיר לי, פעם במבחן בקוונטים 2 הבאת לנו פוטנציאל יוקאווה. זה איכשהו קשור לזה? זה?
זה פוטנציאל יוקאווה. עכשיו, now why... well, let's translate. Is this connected to Yukawa potential? The answer is yes. Now, how did one get to Yukawa? How did Yukawa get to Yukawa's potential? There's nothing really in nature that actually follows Yukawa potential. Let's say it first state. Second, you can get Yukawa potentials because of mathematical problems. Here we put in this epsilon not equal 0, which gave us an What is a Yukawa potential? It's like a Coulomb potential, but at long distance it's multiplied by exponentially, which effectively cuts it off. Okay, why should it be cut off? Well, first of all, because it's more convenient mathematically to treat, and then we do a song and dance at the end why it's justified. Here, the song and dance is this positive jelly. But Yukawa got to it from a completely different angle, and that's strong nuclear interactions. Strong nuclear interactions were known to exist already, basically already by Rutherford, but in the 20s and 30s it became clear. Why is that? Because, simple. What is the model of a nucleus? A lot of positive charge together. The same arguments that I gave a few minutes ago about electrons is correct also for these protons. They should run away to infinity and not stay as a nucleus. The only other force that people knew at that time, gravity, would not have been strong enough to hold this nucleus together. Okay, so it was clear that there is some force that keeps these protons together. What else was clear? The other thing that was clear is that this force can't be long range. Why? For the simple reason, there's an upper boundary on the size of nucleus. We know there are only around 100 elementary atoms. And basically, once we try to push above uranium, these atoms disintegrate. They just don't hold together. So the conclusion is it's probably a short range force. What's the simplest way to put in a short range force? Take the Coulomb and multiply it by exponent. And give the prefactor of the exponent as something that is inverse the radius of a typical nucleus, so a few angstroms. Actually, sorry, a few 10 to the minus 14 meters. That's the Yukawa potential. Afterwards, it was understood that it comes from a deep physical reason. The particles that mediate the nuclear force QCD actually has mass, and massless particles like photons have long range interactions. Short particles that have mass have short range interactions. They can't go very far. Okay, so that's Yukawa. Okay, so I want to repeat this game for one-dimensional systems. Okay. And this is extremely difficult for the simple reason this diverges actually at 0. So one solution is, look, let's replace that. By a short range cutoff. Yes, please.
What are we describing? The potential?
I'm going, if you remember the derivation of VQ that we did in the last lecture, it was done for 3D. You remember Q? I'm now looking what happens in 1D because as I started, I'm interested in introducing the Latinger model, Latinger liquid, and that's a one-dimensional model.
Just a reminder, V is the potential?
The form of the potential. So that's basically that's the potential, and that's the Fourier transform. And we can't do the same tricks that we did for 3D for the simple reason that basically the problem here is not necessarily at large distances, it's at small distances. So one way is to cut off the small distances. That's a mathematical trick. It can be done. If I do this thing, I end up with So we get here a Bessel function. Okay, that's a mathematical solution. Actually, a physical solution is understanding that in 1D we don't have electromagnetism. Indeed, if I'm thinking about electrons living in 1D, right? The electrons could be restricted to 1D, meaning they're living only on this line. How is it done? Nowadays, with all kinds of games, from things that you know from cold atoms to things that you know on depositing gates on two-dimensional electron gases, you can restrict the electrons to 1D. But the electromagnetic force lives in 3D. So the power lines between them is nevertheless a 3D case. Another thing that happens and usually plays an important role in these cases is that basically to restrict something to 1D, you'll have image charges, because the gate is a metal, and you have if you put any kind of a charge near a metallic gate or a metallic just a piece of metal, you'll have an image. So it's much more complicated than this simple description. Therefore, this description from the beginning is not relevant. But just if you insist on doing electromagnetism in 1D, you'll have to put in a cut. Okay, but that's not the main topics that we are looking into. This is just a side remark, and let's move to okay, so let's write down the Hamiltonian, which is exactly the Hamiltonian that we have seen previously. Exactly the same Hamiltonian that I've written before, with one obvious difference and one that I would like to talk a bit about. The obvious difference is K is now doesn't have Kx, Ky, Kz, it's just one dimensional. So K in this game will be or if I'm talking about cyclic boundary condition, Okay, so that's K. Just one number, not three, as in the previous. The second interesting thing that happens, which is something that is done a lot in condensed matter, is putting in the Fermi energy. What does that give you? Somebody can give an explanation why I put it here? Or perhaps a step before it. Where have you seen such a form in thermodynamics, in statistical mechanics? Yeah, but something much more basic. Ensembles. Canonical ensemble, you have a fixed number of electrons. So basically when I'm writing something like that, I have to tell you, you have here n electrons. You have also grand canonical ensembles. What does that say? Tells you, look, I can tell you what is the average number of electrons in this system. And there you had mu, the chemical potential. Here, this term exactly plays the same role. Basically, it tells you that it has a defined number of electrons. Sorry, not an average number of electrons in this system. If Fermi is large, I have many electrons. If Fermi is equal to 0, the solution is 0.
Why is it minus?
Exactly for that. As long as it's minus, you get lower energy as you add particles, right? Once you cross above, once h square k square over 2m is larger, you reduce. The energy becomes larger as you add particles, right? So where is the ground state? You fill it up till the point that this guy is equal to this guy, and that's that. Why didn't you see this form in quantum mechanics till now? Because before you had Hilbert spaces, you had a fixed number of electrons. Now you have Fock spaces. You can consider the cases that you have different number of electrons. Right? So here the ground state will be the point that all the states are filled up till Fermi energy. So it looks very innocent, but it gives you a new dimension to what you're doing. Okay, and for Luttinger liquid, it actually plays a very important role, and we'll see it in a moment. Okay, all the rest is the same. Interaction term, and kinetic term. Okay. So if I'm looking on the energy states of the system, the single particle energy states of the system, that's a picture that I see. Okay, now, what's so special about 1D? The Fermi surface is very simple. It's not a surface, it's 2 points. So, the basic idea behind Latinger liquids is stop worrying about what exactly happens everywhere, because as long as we're dealing with low enough temperatures, all the bulk of the states here are not in the game. The only thing I worry about is things that happen around the Fermi points. And as you can see, when I'm moving to 2 and 3 dimensions, it becomes much harder. That's why Latinger liquid works in 1D, basically. Okay, so what do I actually do? Instead of considering K I'm looking on deviations from the Fermi. From the Fermi momentum. So the energies are so because because Q is much smaller than Kf, I don't have to keep terms of Q square, and I'm left with this, where Vf is just H bar Kf divided by N. Okay, so what did I do here actually? I linearized the term. So if I'll call this term H0, meaning the parts that don't depend on interaction.
What's the second sum over?
Q.
Why? What is BF? What is QF?
Just I have Q times KF.
KF, right? You say you write there VF, the Q, then H bar KF, not KK.
Okay, so let's see what I have written. Now I have actually two types of particles that can be created. Particles around this area, this point, and particles around this point. Okay. Particles around this point. What is the direction that they are moving? Right. Therefore, ARQ. Particles around this, they're moving to the left. So I started here with a problem that electrons could move in any direction, but now I'm rewriting. I'm not changing the physics. It's just I'm dividing them to particles moving to the left and particles moving to the right. Why? Because I'm one-dimensional, and around the Fermi energy particles would move either to the right or to the left. Okay, minus here, just simply because in this direction they're moving with minus BF. Okay, so far a bit of work and no gain, because I started with something that I knew how to solve, and I ended up with something that I also know how to solve. Okay, now the interesting thing is what happens to the interactions. So I'm defining an operator So I'm using the index S instead of right and left. And at the moment, this is an operator, no obvious reason why to define it, except that it's clearly a legitimate operator. Okay, my big problem is, of course, the electron-electron interaction. The moment I didn't do anything, just copied it from here. Okay? Okay, being lazy, I didn't copy this whole piece at each of the 4 terms. But what did I do here actually? Yes, please.
Just a tiny question. What's the difference between the first and the second sum?
The fact that I forgot to put a minus.
Thank you.
What is that symbol?
Hmm?
What is that symbol before K?
This?
Yes.
In the vicinity of. Almost equal. Let's look what's happening here. We have K and K prime, right? But as we did for the kinetic part, we said K and K prime are in the vicinity either of Kf or the vicinity of minus Kf, right? So, when I'm summing over K and K prime, I have 4 different cases. K and K prime are in the vicinity of Kf. K and K prime are in the vicinity of minus Kf. One is at Kf and one is minus Kf and vice versa. So that's all I did. I just broke it up to the 4 different regions where K and K prime can be. Q is not equal 0 because of the positive Gilliam, the problems that we discussed. Okay, nice. I can break up anything to whatever I feel like. Traditionally, these summations are given Roman letters just so we will remember to what vicinity each one of these summations correspond. Okay, let's try to look more closely. What terms do I have here? Just want to keep. Okay, if K and K prime are in the vicinity of KF, what's the size of Q?
Side. The opposite side.
I started with some Q and Q prime and ended up with Q plus, with K plus Q and K and Q and K minus Q, right? If I'm still in the vicinity of K and K prime, Q must be small. That's the approximation we made. Both of K and K prime remain in the region of KF. Same thing here. On the other hand, if K and K prime are each on the other side of KF, the distance between them is 2KF. So Q must be large, of order of 2KF. Okay, so let's look on the first term, and then we'll understand it a bit better and then see all of them. First of all, why all of them are R's? Because the first case, everything is around KF, all of them are right moving. If you want to convince yourself some more, all you have to do is actually sorry, you wrote double summation, shouldn't be. So I'm just writing here for clarification. And you'll see rearranging them will actually give you exactly this behavior. Okay, because Q is small, it's customary. And you remember with the previous cutoff at short distances that Q equals 0, it's just a constant around Q. So same thing exactly for the second term. For the same reasons for which we obtained 1.
It's G4.
So G4 is opposite, where one particle is on the left and one on the right, so the transfer has to be 2kF. Okay, so at this point, and anyone who's doing condensed, the course in advanced condensed matter will solve it till the end. But at this point, we know that we actually are at a position to solve this problem. Why? All the terms here are two operators. Instead of having 4 operators, I have just 2 operators. What happens with H0? I can also write it in terms of this row, 1 operator. Just Q equals 0 is actually row of right and left with Q equals 0 is just H0. So I took a problem with 4 operators, which was unsolvable, and ended up with a Hamiltonian that has either 1 or 2 operators, definitely solvable. And why did that happen? Because of special behavior of one-dimensional systems around the Fermi points. Yeah.
But you didn't really reduce the number of operators because rho
is just, what is a big difference? Rho is just a density operator. Nothing beyond it. It's as if I gave you a 4 operators that can be written as nk prime dagger. Such a model is always solvable. Actually, we'll see in a short while a solution. Short while, perhaps next lecture, we'll see a solution. As I said, I won't go into the solutions. There's some intricacies here on the way. You're doing a course in condensed. Whoever is doing a course in advanced condensed matter will see the solution till the end. But the basic idea here is we have here a system which can be solved under all these assumptions. Well, we linearized around Kf, said we care only about what's happening around Kf, some assumptions. But under these assumptions, it's exactly solvable.
we don't know the expectation value of rho, so it's meaningless.
I didn't give you a solution. I have shown how sometimes effectively you can take a 4 creation and annihilation operator and turn it into something that's 2, and in this case you can continue. I'm showing it because it's an extremely important model in condensed matter, because it's almost the only interacting model that can be solved. Shortly you'll see something similar done for shortly next lecture for superconductivity. Again, we'll take a 4 operators there. We'll solve almost till the end. Here, just there are a few mathematical intricacies that I don't want to spend a whole lecture going into it. Not in an introduction, not for an audience that at least a reasonable part of it won't do condensed matter. The important thing is just to point out You can, under certain conditions, take an interacting problem and under all kinds of assumptions, turn it into something that is essentially non-interacting. Okay. Okay, now we're going into the bread and butter of condensed matter. What is the basic electronic model that you treated in the course in condensed matter third year in your undergraduate studies? Excuse me?
Free electronic books.
Almost. And I really mean almost, because not free electrons, nearly free electrons. Free electrons in a box, you don't have the main, well, yes, I can say, the main difference between all behaviors of electrons in a crystal and a free electrons, what is it? Band structure. Free electrons, you have just any value of K, any energy is allowed. Put in a periodic potential, suddenly you have bands. And for this mod, that is perhaps, if you remember only one thing from the course in condensed matter, that's what you have to understand, because that gives you insulators, metals, semiconductors. Why are you doping semiconductors and get the whole diodes, transistors, everything? Everything comes down to this basic understanding. Take electrons plus periodic potential, you'll get bands. Now, you have learned basically two main models to treat it. One comes from the limit where you're starting from free electrons and adding the periodic potential as a perturbation. That's nearly free electrons. The other limit is you start from orbitals around the atoms and allow hopping or tunneling between the atoms. That's tight binding. The main assumptions that you get bands is you get it from both sides. It doesn't matter. Where do you use one or the other? Where it's convenient. Now, what are we going to do here? The usual game. First, we want to write down a model of electrons in periodic potential in second quantization, because you have a bit more than one electrons in any metal. Second, I want to put in electron-electron interactions. Why? Not so much for the electron-electron interactions. You were told repeatedly that for metals there's good screening and it doesn't matter so much. Or was something like that told you. Or you just were happy to treat it as non-interacting and everything is okay. And this conclusion is correct. generally. The interesting point is that even under this assumption, magnetic interactions which you totally ignored come out very naturally from putting in Coulomb interactions into this game. And that's already somewhat surprising. And if you're not convinced that well, all of you know that metals are the main feature of metals is that they conduct. But they have another feature that, at least for a large class of metals, is important. They may also have a magnetic response. And understanding from where this stems is the main features that we're trying to do in the next step. Okay, let's at least start. Okay, we have here a lattice, one-dimensional, just because I'm too lazy to start to do 2D and I'm not capable of doing 3D. Okay. So what is we know already second quantization. For second quantization, we have to give a single particle basis. We are dealing here with type binding. Okay, so my single electron states are n, which is the number of the atom at a lattice point, and 1, 2, and so on. What is S? We'll add spin in a moment, but at the moment, if I'm thinking about an atom and I'm looking on its single particle states, so it's not enough to say where is the atom, what is its lattice point. I have to say in what state is it. To increase confusion, that's the N in, let's say, the hydrogen atom. You have N 1, 2, 3, 4, and so on. So S is, N is the lattice point. And S is the state. Very quickly, we'll stop to think about different values of S and decide that we are treating a single band. But in principle, the only way to get in tight binding more than one band is that I'm taking into account more than one state on each atom. So psi ns is just the single particle states, and if I prefer to write it in K space instead of N space, is the distance between the lattice points. And K is equal okay, simple single electron treatment. The only thing that is different than free electrons is different quantization of K. Okay. Okay, why am I allowed to write this? Again, that's undergraduate quantum mechanics. Because this equal 1, an integral over a projection operator. While I'm doing it, I'm a bit more careful. I could have defined from the beginning just a creation operation on a lattice point and ignore all the other points. A lot of times when people, I'm certainly doing it, I'm writing down computer model for such a situation. I just discretize and decide that I'm interested only in the value of the point. But strictly speaking, this psi has some spatial extension. So it's not only that it's existing on a point, it's existing at some distance from the point. So this is just a way to take it into account. Okay, if I want to create particle around point N, I have to create it at some profile around at x values that are around this point and create it with a certain spin. So
C is the creation of the spin.
yeah, I'm creating it with some either plus or minus because it's an electron, it's a spin half particle. I have only two positions, and why I'm putting in spin? Because that's how you get magnetism. Otherwise, you won't have anything. And now I'm just writing a shorthand for it, creating around a particle around NS. This is its meaning. Okay. Of course, the commutation relation, anti-commutation. Why anti-commutation? These are fermions. Simply all the indexes have to be equal in order to get their one, otherwise the anti-commutation is zero. Okay. So at least before we're leaving, let's write the kinetic part of this Hamiltonian. Okay, first of all, why it's the same sigma? Well,
Because it's the kinetic part. It's
yes, there's nothing here that does anything to the spin. So if I started with, on the right side with a spin up, let's write the full. I have to end up with a spin up. Otherwise it will be zero, the matrix elements. Okay, so the kinetic part doesn't do anything to the spin. Almost trivial, but needs to be said. Okay. What can I say about this part? So, usually, this is assumed, although this is not exact. If we are talking about two states on the same atom, right? What's the overlap between them? Zero, because they're orthogonal, because they are solutions of the same. Between two different, it doesn't have to be zero, but it's usually very close to zero. Therefore, I'm assuming that the overlap is only within the same band. Now, what can I say about Mn?
they're not zero.
Right, but if M and N are very far from each other, the atomic state usually falls off exponentially, right?
Yes.
So if M and N are far apart, it usually also goes to zero. So usually it's assumed depends how exact you want to be, so you cut off at nearest neighbors, next nearest neighbors, next nearest neighbors, but usually not beyond that. Yes?
When it is near neighbor,
Mm-hmm.
what is it equal to?
Depends on the
Because-
lattice.
Oh,
Depends on the what is the wave function of the
that.
highest lying electron in the depends on the way on the band structure. Depends on a lot of things. These are just general statements of what we expect from it. We will solve it exactly for nearest neighbors. lattice? No, you don't need Eisenberg. What you'll get here, for those who remember something from condensed matter, is instead of dispersion that behaves like k squared, we'll have a cosine ka structure. And we'll get it immediately. Okay, so basically this is how we treat the kinetic part in second quantization. We forget about different bands. We assume that this term, which is usually referred to as hopping, for the obvious reason you are starting at m, moving to n, you are annihilated at n and created at m. That's hopping. The hopping term is short range, nearest neighbor, or perhaps a bit more, but that's that. The next step would be to incorporate, to do the same trick for the interacting part and see what we get. That we'll do next week. Okay, thank you.
Thank you.